All right, let's get started. Today, we're going to jump right into the fascinating world of data mining, and we'll be using the R language to do it. We're going to be leaning on the great work of Bater Makabelte to break down some really clever algorithms that can turn mountains of raw data into pure gold.
Okay, let's kick things off with a classic mystery. You've probably heard this one before, but have you ever noticed that diapers and beer sometimes seem to be sold right next to each other? I mean, it sounds totally random, doesn't it? Maybe a last-minute grab for some very tired parents? Well, guess what? It's not a coincidence. Not at all.
So, the answer? It's all thanks to a really cool technique called market basket analysis. It's basically how stores dig through millions of shopping transactions to find out which items people tend to buy together. And that little discovery, that hidden pattern, that is pure gold for a business. So how do they actually pull this off? Well, here's the plan for our little tour today. We're going to solve that shopping cart mystery once and for all. We'll look at how these hidden patterns get uncovered. We'll take a tour of some very clever algorithms. Then we'll see how those patterns get turned into actual rules. And finally, we'll see just how big this world of patterns really is.
You know, it all boils down to this really powerful but actually pretty simple two-step process. The whole idea is to sift through this mountain of data, right, and pull out the connections that actually mean something.
Okay, so step one, we hunt what are called frequent item sets. And that's just a fancy way of saying we're looking for groups of items that people buy together a lot. We decide on a minimum number, a threshold, and any combo like, say, diapers, beer that shows up more than that, well, it makes the cut. And once we've got that list, we move on to step two. We create powerful if-then rules. Like, if someone buys diapers, then they're probably going to buy beer too.
Now you might be thinking, wouldn't you have to check every single possible combination of items? And yeah, that would be an absolute nightmare computationally. That's where this brilliant shortcut comes in, called the a priori principle. It basically says that if diapers, beer is a common pair, then it just makes sense that diapers by itself and beer by itself must also be common. It's what lets the algorithm be smart about it, you know? It ignores all the dead ends and only focuses on the paths that could lead somewhere. It makes a nearly impossible task totally possible.
Okay, so keeping that core idea in mind, let's open up the data miner's toolbox. Because there's not just one tool for the job. We're going to check out 3 really popular algorithms, and each one has its own special way of tackling the problem.
First up, we've got the ECLAT algorithm. Yeah, the name's a mouthful. It stands for Equivalence Class Transformation. But all you gotta remember is this one's all about speed.
So here's the really clever part about how ECLAT works. Instead of going through every single shopping cart one by one, it flips the problem on its head. It makes a list for each item, like beer. And on that list are all the receipt numbers where beer was purchased. It does the same for diapers. Then, to see if they're a popular pair, it just compares the two lists and counts how many receipt numbers show up on both. It's so much faster.
Okay, don't get bogged down by the code here. The real magic is happening right in the middle, with this function called merge TID sets. That's the engine. That's the part of the code that's actually taking those two lists of receipt numbers and finding the overlap. And if that overlap is big enough, boom, we've just found a frequent pattern.
All right, next tool on the box, the FP growth algorithm. And this one, it takes a totally different approach. Instead of just comparing lists, it actually squishes the entire data set down into a really compact structure, something called a frequent pattern tree.
The absolute genius of FP growth is how it saves time. It doesn't have to scan that massive database over and over and over again. It only does it twice. Once to figure out what the common items are, and a second time to build this tree. And from then on, all the work, all the pattern hunting happens on this much, much smaller tree. It's a huge deal for efficiency.
And just like before, let's not get lost in the syntax. Focus on the big idea. See how the function fpgrowth calls itself from inside the code? That's a super powerful programming trick called recursion. It's kind of like those Russian nesting dolls. The algorithm digs into one branch of the tree, then calls itself to go even deeper into the next branch, and so on, exploring that compact tree to squeeze out every last pattern.
And for our third and final tool, let's talk about the CHARM algorithm. This one is a specialist. Its whole job is to cut down on the noise and the redundancy by focusing only on what are called closed frequent item sets.
So what on earth does closed mean? Well, think of it this way. Let's say every single time people buy bread and milk, they also buy butter. Every single time. Then the pattern, bread, milk, is kind of redundant, isn't it? The real complete pattern is bread, milk, butter. So CHARM is smart. It ignores the little, incomplete patterns and just gives you the whole shebang. The final results are way cleaner.
So when you look at this code, what you're really seeing is the brain of the operation. These little if statements, the is same tid sets and is superset, that's the algorithm thinking. It's constantly checking, is this pattern just a smaller part of a bigger one I already found? That's how it so efficiently cuts out all the redundant noise and gives you just the good stuff.
All right, let's do a quick side-by-side of our toolbox. You've got eClot, your go-to for speed and simplicity, especially on smaller datasets. Then there's FP Growth, the real powerhouse for huge datasets, because of that clever tree structure. And finally, you have Charm, the specialist you bring in when you want super clean, non-redundant results. Okay, so we've found all these cool patterns, but just having a list of items that show up together, that's not the end of the story, right? We need to turn these patterns into rules we can actually use.
And that's where this idea of confidence becomes absolutely crucial. Confidence basically tells us how strong our if-then rule is. So, let's say 100 people buy diapers, and out of those 100 people, 70 of them also grab some beer. Well, our rule, if diapers then beer, has a 70% confidence. Now that is a strong signal.
And this last chunk of our code, this is what brings it all together. It takes all those frequent patterns we found and then filters them using that min-conf variable, our minimum confidence. It's kind of like a bouncer at a club. Only the rules that are strong enough, confident enough, get past the velvet rope. All the weak, maybe just a coincidence connections, they're left out, and we end up with pure, actionable insights.
So you might be asking, why does any of this really matter outside of a grocery store? Well, it's because this whole way of thinking, this method of finding hidden patterns, it's everywhere.
I mean, think about it. These exact same algorithms are used to analyze where you click on a website to make it better. They're used to catch plagiarism by spotting similar chunks of text. In biology, they're finding critical patterns in our genes. They even help us understand who's connected to whom in social networks. The core idea is truly universal.
And that, right there, is really the heart of the matter. Just like Bothra-Makabal's work shows us, data mining is all about finding the hidden model within the data. It's about discovering knowledge that isn't just useful, but is often totally unexpected, and in the end, something we can actually understand and act on.
So from now on, when you see that weird product combo in the store or get a recommendation online that's just a little too perfect, you'll know there's some serious logic working behind the scenes. And it really makes you wonder, doesn't it? What other invisible patterns, discovered using these very same algorithms, are quietly shaping your life every single day?